In this video, I'll be reviewing some of the basic force equations, and we'll be using that in conjunction with the Fu equals ma equation and some velocity versus time graphs to solve problems. And so this is really mixing together a whole bunch of different things that we've done in the past, just trying to see a sort of new set of problems that are, nothing in and of itself is new, but the way that we're putting things together is kind of new. So to start off with, I'll review these different equations. We've got FFR equals mu Fn. So that's the friction force equation. That's the FFR part. Mu here is what we call the friction coefficient. What that is it's essentially a number that indicates how frictional or how rough a surface is. If something's really, really rough, it's going to have a high coefficient of friction. If you've got a low coefficient of friction, it means there's not a lot of friction, and so something like ice would have a coefficient of friction that was near 0. All right, and so what mu is there is just kind of a measure of how much friction we would have in a given situation. All right, after that, we've got the spring equation, Fsp. For Fsp, we've got Kx here. K is the spring constant. It's measured in newtons per meter. And x is the distance that the spring is stretched. It's measured in meters. All right, so spring constant measured in newtons per meter. All right, and x is how far it is stretched, and it's measured in meters. For the last equation here, we have the buoyant force equation. We've got 3 parts to that. We've got g, which is the gravitational constant. That's 10. Technically, it's 10 newtons per meter, 10 newtons per kilogram. All right, but we don't often look at the units on that one. For that thing that looks like a P there, that's a rho. All right, rho is the density, and it has to be in kilograms per meter cubed. All right, and then lastly, we have the volume here. And for both the density and the volume, we're talking about the fluid that's displaced. All right, and that V is volume, and it's measured in meters cubed. All right, so we have to be careful to have everything in the right units here, because if it's not in the right units, you won't get the correct answer, so be careful about that. So hopefully after that cursory review, you'll be good to go on the equations that we'll be using in these problems. Typically speaking, we usually do an Fu equals ma somewhere in here, and sometimes there's a velocity versus time graph involved as well. So this first problem, it says we've got a 0.8 kilogram ball submerged underwater. The ball has a volume of 1,000 centimeters cubed, and it says assuming that the water has a density of 1020 kilograms per meter cubed, find the magnitude and direction of the ball's acceleration. Something important to note here is, based on the way this problem is written, we don't know actually necessarily whether the ball would be accelerating downward or accelerating upward. If we had, for instance, a ball that was made out of lead, that lead ball would sink. Okay? If you have a low density ball, the ball will float. And so we have to kind of plug in some numbers before we really know whether the acceleration would be up or down, but we can figure it out eventually. A good place to start out with on these problems, I think, is to make a force diagram. On this one, there are 2 forces involved. We've got a gravitational force, which is going down, and we actually can figure out the value of that right away. It's a 0.8 kilogram ball, so that means that the gravitational force is 8 newtons. The other force we have on this is a buoyant force, Fb. All right, we don't know what that is yet. All right, and that's where we get to our force equations. We can actually calculate this with what's given. One thing to comment on here, though, is we're given the volume here, but the volume is given in centimeters cubed. I mentioned above, but volume needs to be in meters cubed. Normally, when we go from centimeters to meters, you move the decimal place over 2 spots. But we need to do that for each of the dimensions because it's centimeters cubed to meters cubed. So we need to move the decimal place over 2 spots for each of the 3 dimensions, which means we end up moving it over 6 spots overall. All right, which means that we end up having here, instead of 1,000 centimeters cubed, we end up having 0.001 meters cubed. Something to be thinking about because we have to make everything in the right units. If you have any further questions about that conversion, come in and ask me and I'll explain it to you. So we know that we've got 0.001 meters cubed here in the end. So we can calculate now our buoyant force. It's equal to the gravitational constant, which is 10 times the density of the fluid, which is 1,020 kilograms per meter cubed, times the volume in meters cubed, which is 0.001. You multiply those things together, you get 10.2. All right, so that means our buoyant force is 10.2 newtons. Okay, which tells us the upward force is larger, which means this thing is going to be rising. All right, to calculate the acceleration, all right, we need to think about our, actually, before we write that, we need to be thinking about our Fu equals ma equation, right? So Fu equals ma. Our unbalanced force in this case, there's 8 newtons down, there's 10.2 newtons up. That's unbalanced. It's unbalanced by 2.2 newtons. All right, so our Fu is 2.2. The mass of the ball is 0.8. All right, and then times acceleration. Divide both sides by 0.8, and we get that acceleration equals 2.75 meters per second. All right, and then as one last thing here, I asked for the direction as well. It's going to be in the upward direction. It will be accelerating upward. Problem number 2, we have a box. This is kind of an interesting problem, but there's a box. It's hanging from the ceiling of an elevator. It's attached to a spring. All right, and so I know not the most normal problem in the world, but we're going to try and use a bunch of these equations all at once, and it's another elevator problem, so I think it's helpful to practice those, and I just think it works for a lot of different things. Okay, so here, the first thing we do, again, we're going to make a force diagram for the box. There are really only 2 forces acting on the box. There is the gravitational force, which we know is 50 newtons, because it's a 5 kilogram box. All right, and then there is a spring force, Fsp. In this first case, it says the elevator is at rest. If the elevator is at rest, that means we are at constant velocity, which means that the spring force equals the gravitational force, and they're 50 newtons each. I asked you for each A, B, and C to determine how far the spring was stretched. And so what we have to do here is we have to say Fsp equals Kx, all right? And we know the spring force is 50, all right? I gave you in the problem up above that K equals 250, and we want to figure out what X is. We divide both sides by 50, and we get X equals 0.2 meters, or if you want to put that in centimeters, which might be a little bit more normal, it's 20 centimeters in the end. All right, so either one of those is acceptable, 0.2 meters or 20 centimeters. For B, we have an elevator that's at the top floor and it begins going down, and it says the acceleration is 2 meters per second per second. Something important here is that we realize what direction the acceleration is in, because if you're at the top of an elevator and you start going down, the acceleration is downward, which means the larger force needs to be downward. And I'll come back to that in just a moment. Because what we have here is, again, we've got Fg, and I said the larger force needs to be downward, so we'll have a smaller Fsp. All right, Fg is equal to 50 newtons again, because it's dependent on the mass, and the mass of the block is 5 kilograms. Fsp is going to be a little bit smaller because the larger force needs to be down because the elevator is accelerating down here. To figure out how much of a difference there is, we can use Fu equals ma. In this case, the mass is 5, the acceleration is 2. All right, so the unbalanced force is 10. This means that the upward force and the downward force differ by 10. All right, the upward force is smaller, so it's going to be 10 smaller, which makes it 40 newtons. Then once we have that, we know that Fsp equals Kx again, just like the last problem. All right, which means we know that 40 equals 250x. And if you solve that, you should get that x equals 0.16 meters or 16 centimeters. Either one of those is all right. For C here, now we're at the bottom and it's slowing down. And so this one's a little bit trickier. If you're getting to the bottom of your motion on an elevator and you're slowing down, the elevator car is moving downward, but because you're slowing down, that means the acceleration is going the opposite direction, so the acceleration is upward. So in this case, if acceleration is upward, the upward force is larger than the downward force. All right, so we've got Fg here, and then as a slightly larger force, we have Fsp, because we know it's going to be bigger because it's accelerating upward in this case. Gravitational force, again, is 50 newtons because the mass has not changed. It's still a 5 kilogram block. Then we do, again, Fu equals ma. In this case, again, the mass is 5. The acceleration is 4. We multiply those together, we get 20 newtons for our unbalanced force. That means they differ by 20. The upward force is larger, so that means it is 70 newtons. All right, and then we do that Fsp equals Kx thing again. In this case, the Fsp is 70, K is still 250, and then we're solving for x. On this, we get x equals 0.28 meters or 28 centimeters. Okay, this next one, we've got a boy who's pushing a 10 kilogram box of toys across the floor. It says he lets go, and the box slows and comes to a stop. While it's slowing, the acceleration is negative 5 meters per second. Use this information to find the coefficient of friction between the floor and the box. So it's really important that you know, actually, that this one all takes place after the boy stops pushing the box. That means that there are really only 3 forces acting on it. We've got our up and down forces, our normal ones. We've got Fg, all right, we've got Fn, all right, and then we've got a frictional force, which is slowing this down. All right, Fg, because it is a 10 kilogram box, is 100 newtons. Fn, because it's not accelerating in the vertical direction, is also going to be 100 newtons. All right, these two are the same. To figure out friction, we have to think about the acceleration. We know that Fu equals ma. In this case, the mass is 10. All right, the acceleration is negative 1.5. We multiply those together, you get negative 15. All right, and this is one of those cases where that negative 15 here actually just indicates that that force is going in the negative direction. And so we know our friction force is going the opposite direction that the box is moving. So I'm not going to write negative 15 here. I'll just write 15. And the fact that this is going to the left is implicit that the box is going to the right, and then the friction force is opposing it. And so that's where the negative comes out. All right, and so what we'll do here then, now that we've got friction force and we've got normal force, we know that FFR equals mu times Fn. All right, and so just plugging in numbers here, we've got 15 equals mu times 100. Divide both sides by 100, and we get mu equals 0.15. And then friction coefficients don't have any units, so 0.15 is just our answer. Okay, on the back here we have 3 more problems. These ones are all actually going to involve velocity versus time graphs, so they're a little bit more complicated than the first 3 that we did. It says we've got a 10,000 kilogram train. It's being pulled forward. It's a train car. It's being pulled forward by a spring. It says the train car started from rest and accelerated uniformly, covering a distance of 250 meters in 15 seconds. Find the spring constant for the spring, given that it's stretched by 50 centimeters as the train accelerated. Now here, this is one of those ones where it's kind of hard to know where to start right off the bat. You can make a force diagram, I think, just generally speaking, is pretty much a good first step. On this train car, we've got Fg. We know what that one is. It's equal to 100,000 newtons because the mass is 10,000. All right, which means we've got also here a normal force. And because it's not accelerating in the vertical direction, this is also going to be 100,000 newtons. and then we've got the spring force, which is pushing it forward. The problem here is we don't have K, all right? In fact, I'm asking you to find the spring constant, and we do have how far it's stretched, but we don't have Fsp, and so having two things unknown there, we can't calculate the spring force right now. So what we're going to have to do is try and think then about the motion parts of this, and so I'm going to make a velocity versus time graph, because we actually do have enough information to fill out a velocity versus time graph. We're going to assume that this started from rest. All right, it's accelerating uniformly. I say that it covers a distance of 250 meters, and I say that that happened in a period of 15 seconds. And so one thing we can do here is we've got the area of that triangle and we've got one of the sides. And so I'm going to call this here my change in velocity. On this side, it's unknown right now, but we know that 1/2 times 15 times our change in velocity equals 250. Solve that for change in velocity, and you should get that your change in velocity equals 33.33, etc., meters per second. All right. So this side here ends up giving you 33.33. All right, and then what we can do is we know that acceleration equals our change in velocity over change in time, which equals 33.33 over our change in time, which is 15. And you calculate that, and you get for your acceleration 2.22 meters per second. The reason that's helpful is because then we can do an Fu equals ma. The mass is 10,000. The acceleration is 2.22. All right, and so you end up with Fu equals 22,200. All right. So this here then, we've only got, so since the normal and the gravitational balance out, our Fu is our Fsp in this case. All right, so this is 22,200 newtons. All right, and what we can get from there is we know Fsp is 22,200. We also know that Fsp equals Kx. All right, so 22,200 equals K, in this case, is what we're trying to find. And it was stretched by 50 centimeters, but it's important that we get that to meters, so it's 0.5 meters. All right, divide both sides by 0.5, and you end up with K equals 44,400. 44,400. And the units on spring constants are newtons per meter. Right. You might have, depending on your rounding, gotten some variant of this. If you do it exactly, it's 44,444. All right, but I've rounded a little bit in my solution. Going on to problem number 5. This is a driver of a 1,000 kilogram car sees a small child enter the road and slams on her brakes. The driver was initially traveling 35 miles per hour, which is 15.6 meters per second. If the kinetic coefficient of friction between the tires and the road is 0.7, and the child is 25 meters away, will the driver hit the child? So in this one, it's weird because there are actually a couple different ways that you can go about it. You could use the 25 meters away and see what the acceleration would have to be to stop there and compare that to her acceleration. However, I think the easiest, most straightforward way to do this is just to see how long it would take her to come to a complete stop. And so what we're going to do is we're going to kind of ignore this 25 meters away until we get to the end of the problem, and we're going to see how long it takes her to stop, and then compare that to the 25 meters. And so here are a couple things we can do. First, I can make a force diagram. There's a gravitational force, Fg. is a 1,000 kilogram car, so it is a 10,000 Newton gravitational force. We also have a normal force here. Fn is going to equal 10,000 as well, because it's not accelerating in the vertical direction. And then we've got a friction force slowing us down here, and we got to figure out what that is. All right. We know, though, that FFR equals mu times Fn. All right, and in this case, we actually have both of those. The coefficient of friction, it said, was 0.7. All right, and the Fn is 10,000. All right, which means that the frictional force is actually equal to 7,000 newtons in this case. All right, and so if we've got a 7,000 Newton friction force, and that's our Fu, we can actually figure out what our mass times acceleration is, or what our acceleration is, because we know Fu equals 7,000 in this case now, which equals mass times acceleration. All right, so that means 7,000 equals 1,000 A, and we end up with A equal to 7 meters per second per second. Okay, now we can make a velocity versus time graph. And as I said, what I'm going to do is I'm just going to calculate how long it would take this woman to stop. All right, so what she's doing is she's going from 15.6 meters per second on our velocity versus time graph here. Going from 15.6 down to 0. I know the acceleration here. So acceleration we know is change in velocity over change in time. Or you can simplify that to say change in velocity equals acceleration times time. And then what I can do is I can plug in some numbers here. I know that the change in velocity is 15.6. It goes down by 15.6, but I'm just going to leave everything positive here. The acceleration is technically negative too, but as I said, if I just leave everything positive, it will work out. The acceleration is 7, and I want to figure out what the time is. I go ahead and I calculate that, and I get time equal to 2.23 seconds. Then I can calculate the area of this to figure out the distance traveled, and I get distance equals 1/2 times 15.6, just the area of the triangle here, 1/2 times 15.6 times 2.23. And if you calculate that, you get 17.4 meters. All right, and so it takes 17.4 meters for the woman to stop, which means that she does not hit the child because the child is 25 meters away, right? So 17.4 is going to be less than 25, which means the child is okay. Okay, so that is that problem. On this one, this was another similar one for number 6 where there are a couple paths that you could take, but I think that there's one that makes a little bit more sense. There's a lot of information here. I recommend maybe you just pause the video and read it over and try and kind of get an idea of the problem in your head, and then I'll go through and sort of talk about the things that we have going on here. Okay, so here's the deal. We're going to combine, it says, the person and their equipment with the flotation device to try and make it a little bit simpler here. And so the person and their equipment has a mass of 80 kilograms and the flotation device is 2.5. So together, the mass is equal to 82.5. I think that's good just to keep that in mind. And the total volume here of both things, once it's inflated, the total volume is 0.08 meters cubed. So that's something to consider as well. And so what we're going to do here is figure out the forces acting on this person, and then basically it says that this person has 20 seconds after he pulls the cord to reach the surface. All right, and so I'll figure out how many forces, figure out what the forces are, and then figure out how much time it would take him to reach the surface. I think that that's the most straightforward way of doing this problem. There are other ways, though. So if you take another method and you still get the same result, it's probably right. But as I said, I think that this is the most straightforward way. So I'm going to have a gravitational force on this person, Fg, and it's really the person and their equipment and
the flotation device.
Because that mass equals 82.5 kilograms, all right, the gravitational force is 825 newtons. All right, we have to figure out then the only other force on this person is their buoyant force after they pull the cord and get the flotation device to come out. And so we can calculate that here, actually. We know Fb equals G times rho times the volume. In this case, that's equal to 10 times 1050 times the volume, 0.08. When you calculate that, you should get 840 newtons for the buoyant force. That tells us here then that the unbalanced force, Fu, equals 15 newtons. And then we can use Fu equals Ma. We find that 15 equals, the combined mass is 82.5 times A. Solve that for A, and you get A equals 0.18 meters per second. Okay, which is a pretty low acceleration, but you have to remember that when somebody is coming up from the surface, coming up from underwater, they need to kind of go up more slowly, both just so that they don't physically get harmed and also because of things going on with the pressure and things like that. So we've got our acceleration. I want to find actually the amount of time that it takes to get to the surface. And so what I've got here is one of these problems where I'm going to make a velocity versus time graph. I've got the acceleration. The surface is 50 meters up. And so we know that this is 50 meters. I'm going to call this t, and the change in velocity on that vertical part of the triangle is acceleration times time. Change in velocity equals acceleration times time. And so this is going to be 0.18 t. All right, and so then what I know is 1/2 times t times 0.18 t equals 50. Solve that for t, and you should get that t equals 23.6 seconds. Okay. Unfortunately, 23.6 is greater than 20. All right, so he had 20 seconds sort of that he could survive without the air. And so we know then from this that the man does not survive. So I know that those are quite a lot, those problems. There's lots of different things involved in them. You've got the force equations, you've got Fu equals Ma, you've got the force diagrams, and then you've got the velocity versus time graphs. So it's a lot to keep straight, and that's why we've been kind of building and building and building on things throughout the year. If any one part of this is giving you trouble, then it kind of is like the weakest link in your chain, and so you'll need to brush up on whatever's confusing you here. If after watching this, of course, as with anything, if you're still confused, please come in and ask, and I'll try and help you get in shape. We'll do more practice of this in class, and then eventually you know, by the time that we have quizzes and tests, you need to be good to go on this. So just make sure that you're taking responsibility and trying to figure out how to do these as soon as possible.